All right, so here we go. There we go. Okay, so today we're going to talk about what's it? PCA. So PCA and dimensionality reduction. I said this was my last cohort that I just had. I said this will not takes too long, but who knows? Maybe it'll take us a whole hour and stuff like that. I will say that PCA is a really interesting kind of introduction to unsupervised learning. So I'm actually going to skip over the idea of unsupervised learning because we're going to talk a lot about that next week with clustering. And that's in my opinion, this is, curriculum's a little different from what I have. In my opinion, clustering makes a lot more sense for unsupervised learning versus PCA. I think PCA makes it a little harder to think about, like, what do you mean by unsupervised learning? But PCA is super important because it's not just an unsupervised learning algorithm, which we'll learn more next week, but also it is a great pre-processing tool. So if you guys remember all the way back to like Mod 1, when we did that first project, and what was the, let's see here. I'm just gonna say, remember multicollinearity, right? And do you guys remember what I said, like, when you found something that was multicollinear in the correlation matrix, what was do you guys remember like what advice I gave and like maybe overall what I said? I said it so many times, I don't know if you remember or not. But I think, what was the strategy that we used in that project that we found something that was multicollinear?
I feel like I think we removed one or two of them.
Mm-hmm. Yeah, that's right. I think that basically the strategy I said is like you can drop one of the features so they're not basically enhancing each other and stuff like that. And then if you remember way back, I know it's been like months now, but I mentioned too, like, this is not necessarily the best way to do it. And in fact, we're going to find better ways to approach this and making sure it's, what's it called? Addressing that correlation. This is today. So section, was it 37? Took almost like an extra 20 sections to get to this point. But that's kind of what we're going to talk about with PCA. So it's kind of that. Okay. So yeah, kind of fun. It's in the past, or it relates a lot to the past. So let me go ahead, and I'm so sorry, I don't have everything set up, so I'm kind of just moving some windows around while I talk with you guys. But PCA in particular will actually, what's it called? Relate to something called dimensionality reduction. And so dimensionality is actually a really interesting topic from a mathematical perspective of like why it matters so much. So I'm going to share my screen here, and then where did you guys go? There you are. Oh, Zoom loves to mess my windows around. Okay, so I'm going to just expand this out. Okay, so this should be in the machine learning notebook under PCA, but note that I might kind of update this a little bit too, so the fork might actually end up being a little bit more updated from what you see today, but we'll go from here. So one thing about dimensionality is that, how do I say this? There's a few things about it. One is that when higher dimensions happen, you have the possibility of having more space in between different points. So if you imagine, for example, you have 10 features. 10 features corresponds to a 10th dimensional space. Okay, just like if you had 2 features, you can graph it onto a 2-dimensional plane, right? So if you imagine 2 features, I have my, I'm going to call them like x1 and x2, right? And if I had 3 features, well, then we would have a 3-dimensional plane. So you have this like x3. Okay, so basically the number of features correlate to how many dimensions you have. The thing is, then I'm going to go back to 2D just because it's a little bit easier for us to draw. If you imagine me trying to draw little points here, I'm actually going to try to draw a little point. Okay, there's only so many ways they can vary from each other, right? So what happens though, as we add more features, there's more ways for them to vary from each other. And this correlates to basically them being very far apart from each other in like absolute sense. So if you imagine like in 3D, like, I'm trying to think of a good analogy. This is a tough one to kind of wrap your head around. But like, if you imagine taking like a square in 2D, right? You can probably measure things like, oh, how much area it has, right? And versus how much the perimeter is. However, if you did something equivalent to something like in 3D, so for example, if you have like a cube, oh, that's an awful cube, but you guys get the point. If you did something similar, you did the volume compared to surface area, what you'll find is that you actually get a lot more volume than there is in surface area. And this surface area kind of corresponds to how many dimensions there are. And the volume is kind of saying how much space there is between different points.
Hey, Victor, I had a quick question about this. So
yeah.
I was reading through the curriculum. They give an example of like having 1 million dimensions. Just conceptually, I don't even know what that means. Like, I feel like they kind of used dimensions and the number of features, like they like use it interchangeably, but I know they mean different things, obviously. I was wondering if you could, like, I don't know, clear up what they mean by the number of dimensions, because I just feel super confused about it.
Yeah, so this is actually a good one. So I will say is that you're actually right on there, is that the features and dimensions are actually the same thing. When we say number of features and number of dimensions, it actually does mean the same thing. And that's kind of like—
why is that though? Because can't you have a certain number of features in 2D space? Like, I'm confused as to why they're interchangeable. Like, I thought dimensionality was separate from like the number of features you have.
Can you say that first part again? You said the number of features in two-dimensional space?
Like for linear regression, for example, right? Like, you had a bunch of features, like a bunch of variables to try to, you know, figure out what, you know, our target variable is or what our label is. Is that analogous with the number of dimensions?
Yeah, it actually turns out, we pulled a fast one on you, is that on linear regression, you are actually using multiple dimensions. So like, if you had just a simple, like, this is y, like our target, and this is like x right here, we have some value I can't draw, ax plus b, right? So basically A is like how long you feel in here, B is basically your like y-intercept, and it would look something like this. The thing is, like we said, like for linear regression, you can have something that looks something more like y equals, y being our target, let's say like a1 times x1 plus a2 times x2 plus b. And this actually is a mathematical shape. It is not, it turns out to be a, it's not a line. Does anyone know what this shape actually is? It's a 3D, or I should say it's a 3D shape. So this is a 1D shape, right? Our line right here.
Is it a plane?
Yeah, that's right. It's a plane. So it's like a piece of paper. And essentially we're finding the piece of paper that does the best to fit on these different points. And as we add more and more features, we actually are, in a sense, like, if you imagine like this y, a1, x1, x2, right? This is our y right here. This is our x1. This is our x2. And essentially we have like, if I'm not going to do the greatest job here, but like if you imagine you have something like a plane, like a piece of paper that exists in this three-dimensional world, right? Three-dimensional meaning x1, x2, and y, right? This right here is still a 2D object, x1 and x2, but it's within the three-dimensional space. And that three-dimensional space is really just defined with how many targets and features we have.
Well, just to be clear, like when we did this with linear regression, we didn't really, we didn't deal in, you know, 3D or more dimensions, did we? Because we didn't have like an A1 x1 plus A2 x2. We kind of, or did we?
Yeah, we did actually. Yeah, it turns out we were using it. If you remember back, like, I won't pull it up necessarily, but if you remember back, like when you did like using OLS for stats models, it would have like a nice little like table. And you remember like there would be like some like chart right here, like, oh, like this is like, I don't know, number of houses, right? Or something like that. So houses, and this one, or number of houses, like number of rooms or something like that, right? And this was something like, oh, number of bedrooms. And then this was something like, I don't know, square footage. And then you would have on here was, we had something like p-value that we kind of ignored for the first thing, but we also had a coefficient. Do you guys remember that, kind of like seeing that table? Okay, that coefficient is literally, it's like saying, oh, if this is x1, this is x2. Sorry, my writing's really bad, guys. But x3. And let's say this coefficient was like, oh, this was like 4. This was like negative 3.2. This was like 10. That is essentially saying it's 4x plus, well, negative 3.2. Oh my gosh. Sorry, wish my handwriting was a lot better right now. Plus, what was that, 10? Plus 10x3 is equal to the target, which in this case, we could just call it y. So it turned out that we were actually using multiple dimensions. And this is actually why you couldn't just simply plot out all the features all at once, because if you try to plot all the features at once, there isn't really a way to do that. If you remember, we had to actually plot out a two-dimensional graph for either correlating two features together, or more likely the target, the housing price, if you remember that project, and whatever feature we were looking at. And then we would draw, like, you see the dots right here, and then we would have a line that goes through it. And that line's actually just like if you mentioned the three-dimensional, two-dimensional plane kind of deal, it's like looking at that piece of paper straight on. And that's why it looks like a line, because we're basically ignoring that other dimension that would stick out this way.
So do people actually try to plot out more than like 3 or 4 dimensions?
No. Well, this is where it's kind of fun, is that dimensionality reduction turns out you can do something like this, where you can take, how do I say this? There's a couple ways you can do dimensionality reduction, but one thing you can do is actually try to plot out multiple dimensions onto a 2D or 3D shape. This is something called a manifold in mathematics. I don't hear too many data scientists actually use the word manifold, but this would be something like, we'll talk more about this, but I'll just quickly mention one thing, TSNE. I hear some people say TINSTI or TISNE. I just call it TSNE because I can't try to pronounce this. And so what this is basically, it's projecting, actually, it turns out, like, you can see all these different like labels. It turns out we can take something that is multiple dimension and essentially what we call, like, project it down onto 2 dimensions, so we can more easily picture this. But this should actually be something like a 10-dimensional shape. But it's easier for us to kind of picture in this way. And it helps preserve that the points are close together. Like, oh, like if the points are close together here, they're close together in the higher dimensional space. So this is one way you can do things. Another thing we can do is what we'll talk about with PCA. We can basically say, well, what's the most important, kind of like way of looking at this, and kind of rescale our axis and just plot out those points. Okay. But yeah, in short, you cannot plot over 3D because I don't know if you guys noticed, we don't live past 3D. At least I don't see in 3D. If you go into mathematics sometimes, and like physics and other kind of weird stuff, including data science, you might talk about higher dimensional spaces, but like there's no way, I haven't ever met anyone who can actually picture them in their head in any real meaningful way. The closest thing we have is usually analogies from 2D to 3D. But yeah, does that kind of help out get a little?
Yeah, thank you. That clears it up, because like they were using like 3 or 4 different words, like features, labels, dimensions, and I knew they meant the same thing, but when they said a 1,000,000 dimension problem, I was like, well, I don't know, it just seemed intimidating. I didn't know, but it makes more sense, I guess.
And I think it's one of those things where, to be honest, if you want to intimidate someone or just kind of impress someone, you can say, oh, I was working with a 50-dimensional data set, and people are like, whoa. And then if you said a 50 feature data set, people are like, oh, well, I know what that means. Like 50 columns, it's like, oh, that's all you really mean. But that is equivalent to each other. So just know when you see that, that's a good point in the curriculum or anywhere really. If you see features in dimension, they're really equivalent. And again, kind of like, I try to equate things back to like my physics background, but we talk about dimension. And when we say dimension, we just mean direction. Essentially just another direction you can go into. So a direction, the features say, oh, I can go, number of bedrooms. Okay, I can go 1, 2, 3, 4, 5 bedrooms. But I can also say, oh, how many windows do you have? Oh, I can have 1 window, 2 windows, 3 windows, 4 windows. Those are completely separate from each other. Like measuring the number of bedrooms doesn't necessarily measure how many windows I have. So we say those are different directions, different measures. So they're different dimensions. Okay. Yeah. So I think hopefully that's, I know we spent some extra time on that. I think that's actually a really important part though. So cool. But yeah, this is actually where PCA is one of the strategies of reducing this dimension. So I'll introduce PCA in a second, but I'll kind of show you a little bit like what I mean by dimension. So we're going to start with something nice and easy, 2D, no 100 or no million dimensional spaces today. But we'll start off with something like 2 dimensions. So what this is kind of going through, right now, this is like just random points. And I would argue is that you really can't express this data set, like these values, without using 2 dimensions. Like you have to have an X value and a Y value, right? Go back to like your graphing days in like high school, right? Is that like, this would be something like 0,50, right? For this point. You need an XY value. There's no way to like really summarize this together without saying, you know, without like, you can compromise, right? You could, for example, just say the X value, but you probably really can't like express this in full, the full detail without using 2 dimensions. So compare this with something like a line. So this right here, okay? Now notice here, this is still on a 2-dimensional plane, right? There is, the Y value is, looks like 1,000, or is that 1.0? Oh, it's probably 1.0. Yeah, it is 1.0, okay. So this value right here is on 1.0, but the X value can change. If I told you it's on X equals 30, do you already know what the Y value is? Yeah, and assume that this is all like 1.0, right? Yeah, you would know. Basically, you don't need to say the Y value. So I would argue that this is really a 1-dimensional object compared to over here, or 1-dimensional data. You only need one feature to really describe this full data set. Does that make sense? Okay, so then I'm gonna have something a little different. So this is kind of a mix between the two. I have a line, but it goes diagonal. So note that I can't just simply say, if I say 20, well, in this case, it's just a line. So like, it's just going up by 20. But like, if I had something a little bit different, let's say I did like something, say like 3 times 6. Okay, now you say 20. I can't necessarily just say, oh, it's just 20. That's all that matters. Every point's exactly the same on the Y. The Y changes as well, right? How many, like, if I were to say what kind of dimensional object this is, what would you guys say? Any guesses? And just whatever kind of like what feels right. And maybe a better way to ask this is, what does this line right here look more like? This random data or this like horizontal line?
Looks more like the line, I guess.
It does look more like the line, right? And I would argue that this is actually just like the line. It's 1D. Basically, you can express it with just one variable. And you say, how do you do that? How would you express it with one variable? Well, that's what this equation does. Basically say, hey, if I know what the X value is, I can figure out what the Y value is, okay? And here, it was easy because the Y value was always the same, but it's the same idea. It's like, if I know the X value, I can either figure out the Y value or I already know the Y value. So I would really say that this is a 1-dimensional object. And the way you can kind of think about this too is like, well, really what I have is just, I can just draw a line straight through this. Oops, I can't draw. There we go. I can draw a straight line just right through this, right? And say, okay, well, that is the information. I can kind of like just turn it over and I have this straight line here. So this is the way we can say, even though this is 2 dimensions, right? It's got 2 features, this X and Y axis. I can really describe this with like one, you know, kind of like expression. Okay. Does that make sense to people? Yeah. Okay, cool. So this is going to bring us into the next part then. So, okay, we have another dimension here. We have some line with some noise. So this guy right here, what would you guys say? Is this a 1-dimensional object or a 2-dimensional object? See a 2 from Ali? Anyone else? Okay, and so Ali, can you go explain like why do you say 2?
Because there's no pattern to it, so it looks irregular to me. So it'd have to have more than 2 dimensions or more than 1 dimension.
Okay, yeah, I think that would be like, I definitely think that's a valid argument to say like, hey, there's definitely some like, there's no pattern to like how much noise this is, right? And so I think this is where you can argue either way. Is I think if someone said it's 1-dimensional, I could say, yeah, it's more or less 1-dimensional. There's just some extra noise. But in order to like, I would say, I would actually agree with you, Ali, in this case, is that in order to really understand this data, you really need to have 1 dimension and then saying like, for example, how far off you are from the line. And so essentially we need 2 parts. We need to essentially not just, you could look at just X and Y, but to say this another way, we could say, well, we could figure out what the line is and then to say, how far are you off from this line? in this direction. So in that case, you really need two things. You need to know where you are on this line and how far off are you like above or below this line. Does that make sense to people? Yeah, and I think you could also argue, like I mentioned, you could maybe argue this isn't really one-dimensional. It's just some extra fuzz. But I'd say in order to actually, like we could estimate this to be about one-dimensional, but then we'd lose some information, right? If we did just a line, we wouldn't have the full data set. So we need that extra dimension. Though, let me ask you guys, what probably is more important in this case? How far off you are on this line, so this up and down, like in this direction, or where you are on this like solid line that I drew?
So the line.
I'm sorry, which line?
The line that you drew would be
this
the
big
most
old line.
important. Yeah.
Yeah, right. It's going to describe that data the most. Like if I looked at just like if I did the opposite and just said, there's some line here, and I just said, how far are you off the line? That doesn't give you a whole lot of information because you can see like a bunch of these points are very close to the line. So there's really not a huge amount of information on here. So most of the information is saying, where are you along this, line I drew in this diagonal, okay? So this is kind of what we're going to do with PCA. Essentially says, all right, we're going to use the data we have and try to express this into what gives us the most information. Essentially saying, hey, like what is going to give us the most information? In this case, the most information is going to be gained when we have that straight line right here. Where are you along this line? And then say, okay, then what's the second most important information? Well, really like how far off you are from that line, right? So this is essentially a really great strategy because now we can say, not just saying, X and Y here, or X1 and X2, we can say, where are we on this like new axis essentially? And so we'll kind of see what this looks like in a second. But before we move more into PCA, I kind of want to show one last example. And I'm going to clear this guy. So this guy right here, we have a clearly kind of curvy function. And this is where, you can say, what kind of dimension is this? And remember if I said on the this line here, I would say 1D, I would argue that this is really 2D. Basically, there's not really a easy way for me to describe this with straight lines, essentially saying, where are you on this axis, right? I still need to have essentially this X and Y value to begin with to really describe this part. I think I could see people maybe argue with something like X and Y. So I wouldn't say for a firm like, oh, this is going to be 2 dimensions no matter how you look at it. Because I know for a fact, like in mathematics, you can do something called like parametric plots, where essentially you plot out, where you are in time as you come travel along this line. But some graph like this, where we have a clearly kind of non-linear kind of pattern, we would really call this 2 dimensions. And the way you can kind of imagine that is we have one line that goes like this. Oops. Gosh, I can't draw anymore. There we go. Okay, one line that kind of goes like this. Where are you along that line? And then something similar again, where we have where are we in this direction away from the line? How far are we off of this line? And that's what I mean, like, oh, this really should be 2 dimensions. And that's what PCA will do as well. It will look at this as, oh, this is really 2-dimensional stuff. We can use one line to describe most of the information, and then another line, another axis to say how far are you away from this point? Okay, does that make sense to people? Okay, so I'm gonna go back to this guy right here. And so the main thing for PCA, and to be honest, I think, I don't know, I debate with people about this. I don't feel PCA is actually that bad of an idea. Like I think people get very like say like, oh, this is like the hard, like I've literally heard this is the hardest thing in machine learning to understand. And I don't think it's actually that difficult, maybe to formalize it, it's a little hard to like get your head around it. But I think we intuitively kind of understand is that essentially what PCA does is like, hey, let me draw some new axes. So if I start off with like 2 features, like let's say X1 here and X2 over here, okay? What I'm trying to do is like, well, is there a better way for me to describe this? Like, I could describe each of these points with X1 and X2, but if I could go ahead and describe this line with something a little more informative, that makes more sense. So for example, is that basically what PCA will do is like, hey, let me draw that line through here because this is going to show me the most information. If I know where I am, and imagine this is like the 0 point in this like new axis. So you imagine like kind of like tilt your head over and like that's my new x-axis. Like this is going to essentially be my new, feature. And I say, okay, where am I on this new axis? And you can imagine all these points basically kind of like being projected down. So if I had something like this, let's see, I'm actually going to draw it like this, an example. So say I have my PCA part. Let's say I have like a point like looks like this, point like this, point like this, and like this, and like this. What this will look like if I were kind of like project everything down to that one like straight line, what this will look like, imagine that's the straight line. It'll look something like, here's the first point, the second point, and then like the other 3 points. And that's conveying a lot of information already. Like this tells me pretty well if I knew what this line looked like. This is telling me where it is on that line versus if I had something like, let's say I use blue here and say, okay, I have this other line here and I project it downward. So you project all of these down on top of here. What this line will look like if I tilted it sideways now. So kind of imagine like you take that line and kind of tilt it back sideways over here. What it'll look like is like, oh, we have like a point right here, and then looks like 2 points right here, and then maybe like a point right here and a point right here. And this is going to act like you actually can measure this. Like you say, oh, this actually is not giving us that much more information than compared to like this very long line where it's telling us a large variance, basically how it varies over through. And that's the key part, is that what I just said is the variance, is that if it has a high variance on a certain axis, like in this direction, that means it has more information, right? If it varies a lot more, we need to know more about it in order to describe it. If they don't vary that much, then it's like we don't need that much information, right, to describe it. So what we're doing really is saying, hey, what gives us the most information? What's the most important axis, important, like, you know, what we call like a constructed feature. Like if we made a new like feature essentially that's going to go in this diagonal direction, what's the most important like direction we care about? And that's going to be why we call it a principal component. So component meaning that we're constructing it, right? And axis, so like we can imagine a straight line. And the principal component, so the P of the PCA, is saying what's the most important component of this data. And so that's why we're going to have something essentially, well, we can say this is like the most important one, this red line here, and this is going to be the second most important one. Okay, basically there's less information, there's less variance in here. And like, I think this is the part that I think people get really thrown out. It's like, whoa, like where did this come from? But the important part is to really think of it intuitively from here. Is that if you were to try to describe these points, they really are mostly going across this point, and you really can describe most of the information just by saying where they are on this red line. Versus if I have another blue line like this, I can also say how far they are from this point, like along this blue axis. But that doesn't give me that much information because they're all very similar to each other. They don't vary very much. Does that make sense to everyone? Any questions how to describe this?
So you could essentially draw any line around that 0 point as your component, and then you're looking for whichever line has the points are the most spread out.
Yeah, that's kind of one way you can look at it. Though I will kind of say something right now about PCA is that it turns out these lines and axes can be constructed in a certain way, and they have to be what call orthogonal. They have to be 90 degrees from each other. And the real reason why is because if you have, let's say, I don't know if this will erase their thing. Let's say if I have a line like this, you can say how far they are from this line, but then you notice that that's kind of incorporating some of the information of how they are in this line. So we want to minimize how much information.
So it's like a correlation.
Yeah, it's kind of like correlate. Like how are they like this is correlated too much to this red line. So we want it to be independent. So what's really cool about that though, and this is what's really awesome about like PCA, is that because we have to have them orthogonal like this, they have to be 90 degrees, it means that they don't affect each other. That me measuring how far they are on this blue line and how far they are on this red line aren't correlated with each other by themselves. And we can actually treat them like independent features. So if you hear that, they're like, hey, wait a second, because these parts, x1 and x2, they're clearly correlated with each other. Now all of a sudden we got rid of that correlation. We basically extracted all the important information is along this red line, and there's some extra information in this blue line. And now we no longer have two correlated axes, two correlated features. And that's a huge bonus for PCA. And that's where, if you remember back in Mod 1, I said, oh, if you have correlation, right now we're just going to drop it, but there's better ways. This is that better way. We can get rid of that correlation essentially by making new axes. Does that make sense?
Yep.
Yeah. But good point out on that kind of drawing like another line, right? Because if you drew another line, you could technically do it, but you'll actually be incorporating some of that information from the red line. And it's kind of like basically double counting. And like Andrew, you perfectly said, it's correlated with each other. And we actually want to avoid that. So PCA, if you were to kind of like summarize like what PCA is doing, it's taking these data points and transforming it into onto new axes, and they're ordered by level of importance. So the most important one, we call that like our very first principal axis component. That very first one is going to carry the most information, and then as we kind of break it down into further parts, we'll get less and less importance or less and less variance. So there's less and less much information in there. Does that make sense? Cool.
Does that mean we're always going to have 2 components for each dimension?
Good point. Not necessarily, but most likely yes. So like you can see, if there's any fluctuation in this direction, we have to have a second component, second axis, because there's no way for us to incorporate this information. However, if you did have some data point that looked, or some data that looked like this, if we drew that one component through here, there's no need for a second axis because they're all the same. So you could technically get that second axis, but that axis would be like a constant. So you wouldn't necessarily need. So for example, turns out we'll actually, the way the math works is that we'll actually tend to center it at 0. So essentially that last axis would be just equal to 0. So basically nothing changes.
Got it.
Good question though. But yeah, how should I say, what's the most number of components can you make? What's the most number of components can you make depending on like what your data already looks like? So if I have something like, let's say 100, dimensional, 100 feature, right, data set, what's the most number of components can I possibly have?
Maybe 200.
Turns out I only need 100 at most, because essentially if I had to use 200, right, that means I can have just used the 100 to begin with to describe the data. So that 100 will always be like the number of features will be the maximum number of principal components you need to describe the data. Does that make sense? Okay, give me a thumbs up if that made sense to people. A thumbs down if like, what, you lost me. Okay, I got that feeling from people. All right, so I see some thumbs down. So
yeah, well, I mean, it makes sense when you say that, but when you've said, well, we need 2 components for each dimension, then
we don't need 2 components for each dimension. We need each component is redrawing our axes or redrawing our dimensions. So like this right here is a 2-dimensional data set, right? So like it's x1, x2. So we have to draw, like we can draw our first component, and then there's some extra stuff. So that's our second component. So now we get from 2 features, x1 and x2. And let's say we transform this into our principal components. Now this is like P1 and P2. Does that make sense?
Yeah, so but then we still have 2 components.
That's right. So we still have P1 and P2. But the important part is that now the P1 we know has more information than P2. So kind of jumping ahead, the reason why this nice importance part is that we can say, well, okay, I really want it to reduce the dimensions. I don't want it to be 2D. I want it to be something simple. We can drop one of these components. Which component would you drop if you had to drop one of them?
P2.
P2, because it's got the least amount of information. So now it's like, technically we lost some information, but we lost the least amount of information. So we reduced the dimension with losing the amount. If we dropped, in this case, just x1, well, we're going to lose a lot of information because there was some information along x1. This is basically, by pure mathematics, it basically says, this shows the most amount of information. You can't draw better axes than these 2. And kind of throwing out some jargon that the curriculum also throws through. And I say jargon, I mean like it's very common. These principal components, this P1, P2, are called eigenvectors. And so eigenvectors are basically, I don't know if anyone speaks German necessarily, but, and I don't, but I know from eigen meaning the true value, the true vectors. And the true vectors meaning that this is like, oh, that's like what it really should look like. This is the true dimension. This is kind of the true way of writing the data set. Does that make sense? Mm-hmm. Okay, so note that basically the most number of features you can have are literally the same number that you started off with, right? Because if you had to do more, you could have just used the original data set's features. So that's kind of like the way you can think of it. You can potentially have less than the number of features, right? Just like we saw in here, we only need one principal component, right? P1, and then we don't really need P2 because there's no variance in P2. There's no information left to give. And we can order those P1s and P2s. And if you had like multiple dimensions, like 3 dimensions, you can have a P3 dimension, okay? And what's gonna be true is that this is always gonna have more information than this one, and this one will have the least. Okay. Everyone follow me with this so far overall? Thumbs up if you're feeling good, sideways, thumbs down. Okay. Andrew, see a little sideways, see Hazel sideways. Is there anything I can clear up more or?
So what if we had, you know, a lot more than 3 dimensions? How do you know which ones to keep and which ones not to? Or am I jumping ahead?
No, that's perfect. That's actually a great segue into like what you would do next. I'm going to give a really short answer though. So the curriculum talks about covariance matrix, and you can create this thing called the covariance matrix, basically saying how these different features correlate with each other. In practice, you don't need to calculate the covariance matrix. You don't have to calculate the eigenvectors by hand. You actually can use like sklearn's PCA and actually use PCA to say, hey, here are my data. I want this many components. Give me the most important, like these, like let's say I want the 3 most important components, give me that thing. And it will figure out automatically, essentially with the mathematics, essentially it's figuring out which components to use. That's kind of me very quickly like saying, oh, the mathematics. I'm tempted to show you guys, but I'm also like, it doesn't necessarily help you more by itself. But if you are curious about how this works, it's something called eigenvectors. And there's a whole bunch of mathematics of like how these eigenvectors work and such. But that's really what we're doing with, what's it called, a PCA. We're really trying to find these eigenvectors. And they're really calculated from this thing right here. This A minus lambda is something called the covariance matrix. And we basically can use the covariance matrix to solve for what this vector is supposed to be. And this vector will be the eigenvector. But I won't go into, I don't think it's necessary for us to walk through and everything. If you guys are okay with that, or would you, yeah.
Okay.
Okay. But anyway, so that's kind of like the overall concept. Does everyone understand like the overall concept of PCA? Like what we're trying to do? Okay. All right. So I'm just going to walk through a little bit of like how PCA is used. So I kind of mentioned that one thing you can do is build up, what's it called? You can use it to do dimensional reduction by basically getting rid of your weakest component, basically your component that gives the least amount of information. You can also do this as kind of an interesting idea of combining to get rid of correlations, basically trying to pull out the most independent information from it. So I'll kind of mention about what this looks like. But before I do, like I said, eigenvector, proper characteristic, the true one, right? There's a couple of videos. I think these are from 3 Blue, 1 Brown. I mentioned this before, linear transformations, and he talks about eigenvectors and eigenvalues. He kind of talks about like where this comes from. So if you want to kind of see like more of the mathematics, you can kind of look at this and see how this math is able to figure this out. But in order to do this, you would have to make sure you understand linear transformations, which are basically matrices. And then saying from these matrices, this A right here is a linear transformation, and that can figure out this eigenvector. Note that this lambda here is also part of this eigenvector called the eigenvalue, a special value that allows you to pull out this information. But Again, I'm not going to focus completely on that because I don't think it's necessary to do the principal component. Okay. So this is just kind of a quick review of going through like what PCA does. Basically, we're trying to find that axis, and if you did the mathematics to find this eigenvector, which is the principal component, it will center it along the data. So like I mentioned before, is that it will always have it to start off at 0. So you have this like kind of like balance between like, oh, here's the data on the left, here's data on the right. And you'll always have that balance. So kind of try to center the best way. And it is literally finding the best way to represent this, which is pretty cool. But let's see here. Yeah, I'm gonna skip over. So one thing I think the curriculum kind of mentions, like this is like drawing a new coordinate system with the coordinates being of length unity, meaning length of 1. If you imagine back to here, what we're really saying is like, oh, you can draw these new lines, these new axes, and you can say, okay, this axis is going to be a measurement of 1 unit across each part. And so you have essentially a new way to measure your data on these new axes. But I'm not going to focus too strong on that part. So anyway, the part that you should really remember is that the principal axis, the principal component, is the most important one. And then the spread of the value for each axis, basically that spread is telling us how much information you have, how much variance there is on that axis. And the more variance you have, the more information there is. So the more important one. So you have a more important axis or component. It's your principal component. It's your top component. Okay. So that is kind of like the overview of pretty much what I kind of just said from earlier, but I'm just kind of reiterating to kind of emphasize the points. Now, what's really cool about this is we can kind of think of this intuitively of like what this means. So if you remember back to like when we did our, what's it called, our module 1 project, and we had these correlated values. So I think we even had this exact example. And to be frank, this school ranking and neighborhood safety, this kind of example didn't come from me. But anyway, it's very related to what we have. So we had like something like square foot and number of rooms. You can imagine that this together are probably correlated together, right? Like knowing about houses, you know, if you have a larger house, you likely will have more number of rooms, right? So you can think of this kind of combined together into being something like some arbitrary like idea called the size of the house, right? So you can imagine like, oh, if I combine, like if I were to think of the square footage, the number of rooms, you know, something like that, like maybe even like yard, you know, how big your yard is, that would give some concept of the size of the house, right? This component, this, you know, feature doesn't really exist, right? At least in this data set, it doesn't have, it's not there, right? But you can imagine if we increase the square footage, we'd also increase the number of rooms. So that would give us a size part. I'll argue that you can probably combine this right here, like like how many crimes, you know, for example, happen in this neighborhood or in this zip code, and then how much your like the school rankings in that zip code too. And you might say something like, you know, oh, like for example, this kind of represents like how good the neighborhood is, right? Whatever kind of that means by good. And you can notice that this is kind of like really fuzzy stuff, right? Like how exactly do you measure this together? And actually, I've seen people on the project from like Mod 1 project, wow, taking a long time to spell the neighborhood. There we go. But you can, I've actually seen people try to make this metric. They try to say, hey, can I combine these together and make like a new feature? It does this. And that's actually what Principal Component is doing. PCA is trying to figure out the best feature for you, and literally like the best feature and try to pull this out. Now, in reality, if you give it these like 4 different features with different values, it probably is not going to make principal components that is something called the size or good neighborhood. But analogy-wise, you can imagine how you can combine certain features to kind of make into one super feature, like kind of like a more powerful, more explanatory feature. What's nice too is because principal component analysis can always give you 4 features. Like let's say if you start with 4 features, you have now 4 principal components. You might have something where like, oh, here's the first principal component, P1, and then P2, and P3, and P4, right? So if I were to use P1, P2, P3, P4 for my model, this will contain all the information that was in the original feature set. However, if I want to reduce the complexity of it, right, what could I do?
Drop P4.
Yeah, I could drop P4. I could even drop P3 and just keep it two-dimensional and basically use this and say, hey, this is where most of the information is holding anyway. And you can actually plot this and say, hey, or not just plot this, but also use this to train your model and say, hey, model, these are the most important features. I don't even want to think about that extra stuff because that's probably just noise anyway. Like that's not really giving us that much information. So just look at the main part of these principal components. And that's why if you look at, for example, in sklearns, if you use like PCA, there's an option called N components. So anyone who's done like the lab for section 37, you'll see probably something like to use N components. You can do it one of two ways. One is you can say how many features there are. So for example, or how many features you want. You say, I only want the top 2 features. Or you can say, I only want a certain percentage. So I only want 50% of the features. So you can declare it either way of this way. PCA, at least in sklearns package, you can say, oh, I just want either just 2 features or 3 features or whatever. Or you can say, hey, I want only half of the features. So give me the most important half or the most important 75% of the principal components. And this can reduce your dimensionality, reduce your complexity. It can actually help improve your model because basically you're getting rid of that extra noise that it doesn't really need to know.
Is it only the number of features you can select, or can you say, I want like 60% of the information, however many features that is?
Oh, I get what you're saying. You know what? I wonder if, I actually don't know off the top of my head if you can do something like that. Let's see here. Let's check it out real quick. So this is the number of components I was mentioning about. You might be able to do something like that. I guess not. So one thing that's kind of nice is because this will be deterministic in the sense that your components, remember, there's only the best component, right? What you could do is just say, hey, give me all the components, which is the default, is basically just passing nothing, and say, okay, let me go ahead and start off and see how much variation is from each of those parts. So you could probably automate that part, but it doesn't look like sklearn actually will pass and say, oh, give me, this percentage, whatever that really means of information. Good question though. So anyway, that's kind of like how you would use, how this works, or how you would use it, or why you would use this for doing modeling, or reducing the dimension and everything like that. Does that make sense so far for everyone?
Yeah. Another question. So we had,
yeah,
in the example you're talking about, we have 4 features. And if we decide to go with 2 components, then that's going to be taking information from all 4 of those features, correct? We just don't know how exactly.
That's right. So it's not going to be intuitive. And in fact, in reality, it's probably not going to combine square foot and rooms. It's probably going to combine all 4 in some way that it finds, quote unquote, it finds the best way. And this is why we call it unsupervised, because we're not telling it what to do. We're just saying, do whatever you find is best. And based on the algorithm, it's finding what's best. Note that we're not guiding it into how to find those parts.
Right. So there could be some kind of magical mathematical formula that links square footage and neighborhood safety.
At least for that data set, exactly.
Yeah.
And that's a good way to think of it, is that it's doing whatever is mathematically optimal for that data set, which means you have no control over it. But it means it's also powerful because it means that you will get literally the best one. Now, note that means if your data is not good, it's a little biased or whatnot, then it's not going to perform very well, right? It's because it's going to notice those biases. It's going to say, oh, these are the most important ones. But maybe your data set didn't include some other things that were, maybe it's has a couple outliers, but in reality, those outliers are much more common. Then it's not going to include that information. Say, oh, this isn't a really important feature, when in fact it might be. So at least in the overall population.
Do you get a danger of overfitting to your specific data set then too?
I wouldn't call it overfitting necessarily. I would call it more in the sense of bias, that your data set might not, I guess you can think bias in a sense being overfitting to from the population. So you're using your sample that's not actually a good sample of the real population. Essentially what you have to do, you have that's all you had to work with, well, then you're not going to do very well when you generalize. So I guess in a way, you can say you're overfitting, but I would call it more bias.
Yes. Okay. So based on the data set being biased.
That's right. Yeah. You want basically good data. So yeah, cool. All right. So because again, kind of reiterating when you would use this, right? One is basically what we call these like latent features. So these latent features are basically like, I like to call them like super features. They're features that are combined from the original features to make something else, basically something that didn't exist before. So like mentioning about like the square footage and number of rooms combining together to be like, oh, this is the size feature. Again, I want to emphasize that, you know, if we are using this like in the human sense, the algorithm PCA doesn't know any better about like, you know, what thing to pick. It just knows this is the best thing to pick based on the data. And then of course we can do dimensionality reduction by saying something, okay, give me the most important features and then dropping the other ones. There's a few reasons why you will do, like might want to do this. One is that you can visualize higher dimensions. So if you have something that's a 10-dimensional set, but most of your features are fit within 2 or 3, you know, principal components. You can then plot those principal components and get most of the information of what this 10-dimensional set is looking like. What is nice is that the curse of dimensionality is that if you have many features, you tend to have things to be very far apart. So it can really optimize in plotting these parts in here. But basically it means that you can plot out higher dimensions a little bit easier. Note though, when you do dimensional reduction, you are losing some information. Which might actually be a real reason why. You might want to do this to reduce noise. So you can actually drop those least important components and get rid of most of that extra noise that really didn't affect, like didn't really help, you know, in learning. It doesn't really, maybe just random noise and stuff like that for other reasons. You can do that to help reduce that. And also you can do things like pre-processing. So this is actually really great for like, you know, doing for other machine learning algorithms. So it's very, very common, for example, to do PCA. So you might do something like you standardize your features or your values. So you do like a standard scalar transformation, transform it into basically some value between 0 and 1 or -1 and 1. Use PCA to basically find the best feature, like basically the best features, and then train on those features. And that can actually help you say, okay, like you're getting rid of this noise, but also it can help you actually perform a lot better. Because essentially it has, if it makes an adjustment in one of those principal components, it's going to have like the most amount of information to like really play with, versus if it had to play with X1 and X2 at the same time in order to get that same boost, it's not going to find that as easily. So you tend to have a lot more better performance when you actually use PCA first. So PCA is very, very commonly used as like a pre-processing step. Okay, cool. Yeah, so that's kind of like overall like PCA. Again, the curriculum kind of mentions it more as like unsupervised learning. It is an unsupervised learning algorithm, but it's more commonly thought more as like a dimensionality reduction tool to basically get rid of correlation, to basically improve your model. Okay. Cool. Any questions? I know we're kind of at time, but were there any questions that were kind of lingering that we didn't cover?
Kind of a random question. Can you, like going back to this housing example, so no, square footage is like the most important. Could we keep that and do a PCA on the remaining components,
I could see someone maybe trying to do that. Yeah, you could technically say, all right, let me just use all of these features and do PCA. To be quite honest though, I haven't seen that in practice. And I think that kind of makes sense because when you, by the fact that you are saying square footage is the most important, you also are kind of putting in a bias of saying, like automatically trying to say, hey, square footage is really important, even if the data doesn't say it. But in that case, that might make more sense in the sense you need better data. And that's kind of like the more common approach to it. Because then if you need to say, hey, PCA is not going to find this because you don't have a good examples of this, then even if you were to keep that afterwards, it's still not going to train very well on that square footage feature. So it might make more sense to actually get more data. Yeah, that's a good point. I think that's a kind of an interesting approach that you might think to work, but it turns out it might just be better to get more data. Cool. Good questions. All right, so good. I'll stop it here then, if you guys are cool with that. Yeah. All right.